Hello, Lama. Let's discuss the question number one. Right, this is about the standard enthalpy change of reaction. The Q is equal to mc zeta. Those questions, right, which are appearing at your tute page number 14, right? So let's discuss those two questions, right? First, the question number one. Right. See what they are saying. 0.025 moles of solid sodium carbonate were mixed with 75 cubic centimeters of 1 mole HCl solution. Temperature raised by 36 Kelvin. Calculate the enthalpy change of the reaction for something is given, right? Okay. See what they have done first of all. So what they have done was actually they are mixing two things. One is actually kind of solid Na2CO3. Na2CO3 solid, right? How much? 0.025 moles have been mixed with another thing is added. What was that? That was just HCl solution. So it was 1 mole 75 cubic centimeters. 1 mole 75 cubic centimeters. These two were mixed, and some reaction occurred. Sodium carbonate react with HCl, right? That reaction occurred, right? And finally, temperature change was measured, right? Temperature change was measured, right? So normally these things will be done inside calorimeters, right? The thermochemistry practicals normally will be performed inside calorimeters, right? So calorimeters are some vessels where heat loss to the environment is minimum. In calculations, we take the heat loss to the environment as zero, as these things are done in calorimeters. Calorimeters. Meters are used to measure things. Calorimeters. Calories actually calories are some units for energy, right? So energy measurements will be done with the use of calorimeters, right? Okay. So the temperature change happened. Temperature change occurred is given as what? The temperature change was 36 Kelvin. Delta T was like raised by 36 Kelvin. Raised, right? Temperature increased by 36 Kelvin. Right? The specific heat capacity of water is given for this solution. The specific heat capacity is given, right, as 4200 joules per Kelvin per mole, and density of the thing is also given as 1000 kilograms per meter. Right now, these things have been given. The problem is they are asking about the interchange of this reaction. What is that? Na2CO3 solid reacting with 2 of HCl to produce the NaCl aqueous and CO2 gas and H2O liquid, no? So this is what they are asking, the interchange of this reaction, right? This is what they are asking, the H not R of this thing. Right, let's solve the things, right? So right? When you are to represent the delta H naught R, if you are thinking of delta H naught R, representing kind of delta H naught R, right? That thing will carry a sign, right? Whether it will represent whether the reaction is exothermic or endothermic, exo or endo, the sign. Then it will carry some kilojoules value, magnitude, heat released, heat change. It will carry some heat change. And finally, it will carry some per mole term. So this will represent the amount of reaction. Right? So if you are able to come up with these three things, you are okay with the question, right? The thing is clear. Let's do the solving part. Right, first let's come up with the exothermic endothermic nature of the reaction. So we had seen some increasement of the temperature. So as the temperature is increased, we can say the reaction has released some heat to the solution. As the temperature of the solution increases, that means the reaction has, right, released some heat energy, right, to the solution. That is why the temperature of the solution increases, right? So it's an exothermic situation, right? So we can say the first point, as temperature increased, as temperature has increased, the reaction is exothermic. Reaction is exothermic. So we can say the sign of delta H naught R is negative. Exothermic means the sign is negative. That is okay. Now let's discuss about the heat change happened in this process. Heat change occurred in this process, right? Heat change involved with the process. So there we can calculate the heat here, the absorbed by the solution with the use of Q equals mc theta. For that, first we need to come up with the M, the mass of the solution. Q is equal to mc theta is applied for the solution. So that we have to take the mass of the solution, not of anything else, right? So let's copy the mass of solution. So mass of solution, that is what we need as the M of the Q equals mc theta, as the equation is applied for the solution to come up with the heat absorbed by the solution, the Q. So the mass of solution, to come up with that, we can use the M is equal to dV. So that is going to be density into volume. The density is given as 1000 kilograms per meter cubes, right? 1000 kilograms per meter cubes. What is V then? V, volume. The volume of this thing is going to be 75 cubic centimeters. The volume is supplied only by the HCl. The sodium carbonate is added as a solid. So the volume of the solution is totally given by the HCl. So the volume here can be taken as 75 cubic centimeters. Volume here, right? 75 cubic centimeters. 75 cubic centimeters. So I'll write it here. 75 cubic centimeters. But we need to apply it in cubic meters here, right? So that it is going to be 75 into to the power minus 6 cubic meters. To cancel off the heats, you have to apply the volume, which will be okay with the units of the density. So it will be given as, right, 3 zeros will be cancelled off with this. So it is going to be 75 into 10 to the power minus 3 kilograms. There is a mass there of the solution. So now we can use the Q equals mc theta to come up with the heat absorbed by solution. Absorbed by solution is Q. If it is Q, so Q is equal to mc delta theta. So M is the mass of the solution, that is 75 into 10 kilograms. So we have to apply, right, so it is, I just written this down, 4,200 joules per kilogram per Kelvin. No, sorry for that, right? Kilogram per Kelvin, right? So the C value is given in kilograms, right? So that we can apply the mass in kilograms there for the M, right? So it is going to be 75 into 10 to the power minus 3 kilograms into C is this thing, right? 4,200 joules per kilogram per Kelvin into the K value. The temperature change, delta T or delta T, both are equal, right? In Kelvin or in Celsius, the temperature change is same, right? So 36 kilograms. It's 36 Kelvin, the change, right? So with that, we can come up with the, so I'll write it here. So this will give you the heat absorbed by the solution, right? Let's do this calculation. So 75, so these 2 zeros will cancel off with this, right? Minus 2 will remain, sorry, minus 1 will remain, sorry. So one can say this becomes just 4.2, no? This becomes just 4.2, right? As 3 decimals comes there, right? 75 into the 4.2 into 36, no? So it is 75 into, right, 75 into 4.2 into 36, right? It is given as 11,340 11,340 in joules, right? In joules. So in kilojoules it is, right, 11.340 kilojoules, right? This in joules. So in kilojoules it is 11.340 kilojoules, right? So normally the enthalpy changes will be represented in kilojoules. That is why I have converted to kilojoules, right? Right. That is the heat absorbed by the solution. And we know, if we are assuming all the heat released by the reaction is absorbed by the solution and no heat loss, right, occurred to the environment from here, right, surrounding. So we can say the heat release from these reaction points, or heat release by the reaction, is also equal to this value, right? So we can write like that, right? Assuming all heat released by reaction is absorbed by the solution and no heat loss to the surrounding, assuming that we can say heat released by the reaction is equal to heat absorbed, simply heat absorbed by solution, right? So the heat released by the reaction can be taken as this value, 11.34 kilojoules, right? That is the heat change involved in the reaction. Second part done, right? Final section, then the amount of reaction, right? It is per mole of reaction, so amount of reaction need to be calculated now, right? For that we need to think of the limit reagent as well, right? Let's come up with the amount of reaction, right? I'll erase this thing picture, right? Now we are supposed to come up with the amount of reaction, so I write this thing here. So the reaction is Na2CO3 solid reacting with 2 of HCl, to bring you the 2 of NaClAq plus H2O liquid plus CO2 gas now, right? Let's come up with the amount of reaction here, right? Calculating amount of reaction. So first we need to come up with we need to first identify the limit reagent here, so let's do that. So Na2CO3 moles is given as 0.025, right? Then the HCl moles can be calculated with the use of its concentration and volume. Its concentration is 1 molar, volume is 75. No? 1 mole specific cube, 75 Newton to power minus 3 decimeter cubes, right? That value is going to be 75 Newton to minus 3, right? That means 0.075. Means 0.075, right? So which one is going to be the limiting? So that, right, to react with 0.025 moles of Na2CO3, to react with 0.025 of this thing, you need twice of HCl. To react with 0.025 of this thing, you need twice of HCl. That means just 0.050 is needed, but you have in excess. So this guy is the excess reagent, and sodium carbonate is the limiting. So this is the limiting. This is the limiting reagent. Sodium carbonate is the limit reagent here, right? So now we need to come up with the amount of reaction, right? So let's take the stoichiometry with the limit reagent and the reaction. So Na2CO3, that to reaction is 1 to 1. That means amount of reaction is equal to the amount of sodium carbonate. Amount of reaction is equal to amount of sodium carbonate. So we can say the amount of reaction is equal to amount of sodium carbonate. 1 to 1 ratio, 1 to 1, right? In 1 times of the reaction occurs, 1 sodium carbonate will consume, 1 to 1 ratio, right? So amount of reaction is same as the amount of sodium carbonate, that is 0.025 moles, right? So now we can combine the three things, right? So here it says delta H naught R is negative. Here this says the heat involved in the reaction is this much, and here the amount of reaction is also calculated. With the use of these three things, we can calculate delta H naught R, right? So finding delta H naught R. So enthalpy change of reaction. Delta H naught R, that is equal to minus, right, exothermic 11.34 kilojoules divided by the amount of reaction, the moles value. What is that value? That is 0.025. 0.025. So that value will be given as, let's simplify this thing. Right? So this value will be given as 453.6. 453.6 minus, right? It is kilojoules per mole, right? So this is the answer. Right? That is how we are supposed to solve this question. Right now, the time equation එක solve වෙන්නේ. Right? 6 O in, right? Right now, so complete your answer. Right now, so let's do the second question as well. Right? Right. This is the question number 2. right, appearing in your tute, right, page number 40. Let's do the second one. Question number 2, right, question number 2, right. Let's do the question number 2, right. See what they are saying. So 11.2 grams of KOH was reacted with 100 milliliters of 2 mole H2SO4 solution. Temperature at the start of the reaction and the end of the reactions are given as 23 Celsius and 50 Celsius each. Right. The first thing they are asking is write the balanced chemical reaction for the above process. Secondly, they are asking you to come up with the enthalpy change, the related R, the standard enthalpy change for this change. Right. That is what they are asking. Right. So the first thing is about coming up with the correct chemical equation there. So it is the reaction between KOH and H2SO4, right? So it's acid base reaction, right, between the KOH AQ and the H2SO4, right. Sorry, here they are not adding the KOH as an aqueous solution, they are adding the KOH as a solid, right? So KOH is added as a solid. So KOH solid plus H2SO4 AQ, that is what we are looking at here. So it will give you the salt and H2, the salt K plus and SO4 2 minus, salt is going to be K2SO4 and the H2, right? So first of all we need to balance this thing, H2 liquid, right? So you have two K pluses, right? So need to compute 2 here, and 2 OH minuses combined with the 2 of H pluses to give you 2 of H2O, right? So that is the balance equation, right? It's done, no? So Roman number 2 is all about coming up with the deltation of R value here. Let's do the stuff, right? So what they have done, first of all, let's come up with some picture. So they have reacted, or they have mixed. Normally these things will be done in calorimeters, right? So this is a calorimeter, right? Heat insulated vessel. So we can assume no heat loss to the environment from this one. So to this they have added 11.2 grams of KOH. Some KOH added, 11.2 grams. 11.2 grams of KOH is added to some H2SO solution, right? Some H2SO4 also added, right? H2SO4 solution. The concentration is 2 mole 100 milliliters, right? 2 mole 100 milliliters. To such a H2SO solution, KOH is added. Okay. So this is the calorimeter at the end. Earlier it was the calorimeter at the beginning, right? So some term it is also there, no? Right. So what they are saying is at the beginning, they are saying that temperature was 23 Celsius, and at the end, the thermometer reading they have given as 50 Celsius, no? Right. So that's all, no? So you have solution here, right? So the specific heat capacity is also given for this solution. Specific heat capacity is given as 4200, right? Joules per kilogram per Kelvin. Right? And what other data? Then they have given you the density as well as 1000 kilograms per meter. Right? Okay. Right. That's all they have given, right? First of all, let's come up with the volume as well here. So the volume is provided by only the H2SO4, so we can take the volume of the solution as 100 milliliters, right? That will be needed to come up with the mass of the solution. To come up with the mass of solution, the volume and the right density is needed. The mass is equal to m is equal to dv, right? Okay, so that I have written the volume of solution as well, because the volume is only provided by the H2SO4 here, as KOH is added as a solid right now. Okay, so those that is a picture of the experiment they have performed, right? So let's come up with the let's try to solve the task, right? So basically, again, I am telling you to come up with the delta H naught R. What we need to do to come up with the delta H naught R, the of reaction, right? We need to come up with the sign which gives you the idea about exothermic, endothermic nature, XO endo. Then we need to come up with the right heat change in kilojoules, right? Heat change of reaction. So after that, we need to come up with the amount of reaction as well, right? Amount of reaction. If you can come up with these three things, we are done with the delta H naught R. That is the idea, right? Right now, okay, let's do. So first, let's come up with exothermic, endothermic nature of this thing, right? So first thing is to come up with the sign of delta H, right? Okay, so it is very clear the temperature has increased. Temperature has increased, no? So it's a lower temperature here at the beginning and a higher temperature here. So temperature has increased. So by the reaction, the temperature has increased, right? That means definitely your reaction sites have released some heat, some heat to the solution. So your reaction is kind of a exothermic reaction. That is how the temperature of the solution increased as the reaction sites release, right, that thermal heat to the solution, right? The temperature has increased, so we can say the reaction is temperature has increased of the solution. Let's write that thing as well, of the solution. So that this means the reaction is exothermic. Reaction has released the heat, exothermic. So we can say the sign of delta H as negative. Exothermic means negative, right? Now that part is clear, right? The next part is about the heat change involved in the reaction. Heat change of the reaction. Heat change of the reaction. Right, let's come up with that. So for that, first of all, we need to come up with the mass of the solution, right? And it can be used to come up with the Q equals mc theta, where you find the heat absorbed by the solution that will be equal to the heat released by the reaction, right? That is our pathway here. So mass of solution that can be taken by m is equal to dv, that equation, right? So mass of solution, the mass of solution, right, is actually density into volume. So density is 1000 kilograms per meter into volume. So volume is 100 milliliters. So it should be applied in terms of cubic meters to cancel off the units, right? So it is going to be 100 into 10 to the power minus 6 meter cubes, right? It's a multiplication, right? So that will give you the mass as So you have 10 to power 5 and 10 to the power minus 6 here. So 10 to the power minus 1. So it is going to be 0.1 kilograms, right? So mass of solution. So now we can compute the heat absorbed by the solution. So heat absorbed or heat change of the solution. If it is taken as Q, that Q is equal to mc delta theta, right? So m, the mass of the solution. Mass of solution is 0.1 kilograms. So we have to think whether to apply with kilograms or grams. So just see the right, the C, the specific heat capacity. It is given in kilograms, right? It's given in kilograms. So you have to apply your mass in kilograms, right? So 0.1 kilograms into C is specific heat capacity, that is 1200 joules per kilogram per Kelvin or per Celsius, both are same, into, right, what, delta T, right? So Celsius difference as well as a Kelvin difference, both are same. So this 50 minus 23, the difference 50 minus 23 is going to be 27 Celsius, 27 Celsius, right? So 27 Celsius, right? So it is better to write this thing in Kelvin. The Celsius change, Kelvin change, both are same, right? So I'll write it with Kelvin because to cancel off the units, right? So always the temperature value as well as the mass value should be substituted with units related to the specific heat capacity, right? It is given in Kelvin, so substitute with Kelvin always, right? As temperature change as well as Kelvin change is zero, right? So you can compute this value here. So it is going to be like so 0.1 means 0 will cancel off, 0.1 means 10 to the power minus 1, right? So it will cancel off, right? Okay, so these two will cancel off, right? So you have 420 and it will be multiplied by 27. Let's do the stuff, right? 420 multiplied by 27, right? So that is 11,340. 11,340 in joules. Normally the delta H naught R values will be represented in kilojoules, so we have to convert this into kilojoules. That is 11.34 kilojoules. That is the heat absorbed by the solution. So as we are assuming no heat lost to the environment and all the heat released by the reaction is absorbed by the solution, we can take the same value as the heat released by the reaction, right? Right assumption, assuming, right, no heat lost to surrounding or environment, you can write, let's say environment, and all heat released by reaction is absorbed by the solution. Assuming this, we can say, right, heat released by reaction is equal to heat absorbed by solution, right now. So we can write heat released by reaction is then equal to 11.34 kilojoules, right? It is the same heat absorbed by the solution. Right now, that is done. Next one. So this stage as well as this stage is done. Now we need to come up with the amount of reaction to solve this completely, right? So let's come up with the amount of reaction, right? Amount of reaction. So the third stuff. Okay. Let's come up with the amount of reaction. Right. So for that, first we need to identify the limit region, right? So for that, we need to come up with the number of moles there. So first the KOH moles, that is equal to 11.2 grams divided by its G mole minus 1 value. What is the G mole minus 1 value of the KOH? Is 39 is there, 1 is there, 40, and this 16. It is 56, no? That will give you 2 times, no? So 0.2 moles, right? So for the H2SO4 value, so it's CV, the concentration is 2 mole, 100 milliliters are there. So 2 moles is cube into 100 into power 3, right? Decimeter cubes. CV, clear? So that is going to be equal to what? Right? So 200 into 10 3, that is 0.2, no? So 0.2. So which one is limiting? Which one is limiting? Right? So to react with 0.2 moles here, right? To react with 0.2 moles here, you need just half of the amount of H2SO4, just the 0.1 moles. To react with 0.2 moles of KOH, you need just the half of that amount of H2SO4, the 0.1 moles. But you have 0.2 moles of H2SO4. That means H2SO4 is your excess. H2SO4 is in excess. So that KOH is your limiting. So this is your limiting. KOH is your limiting reagent. Right? It's very important to identify the limiting reagent, right? According to that, the amount of reaction will be decided. Because when the limiting reagent ends, the reaction stops, right? The heat liberation stops, right? Only at that moment, only up to that moment, the heat release is occurred, right? So it's very important to come up with the limit reagent and the stoichiometry of it with the reaction, right? So let's consider the stoichiometry there. So the KOH and the reaction. So KOH and the reaction is with 1 to 2. When 1 times of reaction happens, 2 of KOH will consume. So 2 KOH with 1 times of reaction, 2 to 1. Sorry, 2 to 1. When 1 time the reaction occurs, 2 of KOH will consume, 2 to 1. So that amount of reaction is 2 times, amount of reaction is half times that of the KOH amount. Yeah. So 0.2 representing 2 units. You just need 1 unit. So half into 0.2. Right now? So that means is equal to just 0.1, right now? 0.1. So amount of reaction is 0.1 moles. Right? Okay. So now we have done with the sign of delta H. We have done with the heat released by the reaction, and we have done with the amount of reaction as well, right? So let's combine the three to come up with the delta H naught R, right? Combine three to come up with the delta H naught R. So I'll erase this thing. So the final thing is coming up with the delta H naught R. That means standard enthalpy, right? Change of reaction, and in the change of reaction. Delta H naught R is equal to, the sign is negative, right? The heat change involved is this much, 11.34 kilojoules, and the amount of reaction is 0.1 moles. So the value is going to be negative 0.1, so it is going to be 113.4 kilojoules per mole, right now. So that is your delta H naught R value for this reaction, right? The thing is clear. So just complete this stuff. Right, so that is all with the Q equals mc equations, right, and the stuff, right? So let's complete the stuff, Lamai. Arne, no, other topic, method in right? Okay, complete the notes.